video is on partial pressure. So first let's have a look at what pressure is. Pressure is the force exerted by the particles on a certain area. And this pressure is created by collisions. So this is the particles colliding with each other and the container, creating a force which we call pressure. And the equation for pressure is force over area, and it's measured in kilopascals. When we say changing pressure, it's also the same as saying changing momentum. And momentum is just the quantity of motion. So if pressure increases, we know that the quantity of motion, the momentum, also increases. So now let's have a look at what partial pressure is. Partial pressure is the amount of pressure the molecules are responsible for. So if you have a look here at the Haber process, the partial pressure of nitrogen is the amount of pressure that these nitrogen molecules create out of the overall pressure. So this entire reaction will have an overall pressure, but the partial pressure of nitrogen is the amount of pressure that it's responsible for in that overall pressure. So now we're going to have a look at the equilibrium constant. And an equilibrium constant is the value of the reaction quotient at equilibrium. So quotient is just the word for division, the answer from the reaction division of partial pressures. And so Kp is the equilibrium constant based on pressure. And this is the pressure of the products over the pressure of the reactants. And so now let's have a look at an example. So this reaction takes place at 150 atmospheres. There are 8 moles of sulfur trioxide to begin with, and 2.5 moles of oxygen is produced. Calculate Kp, the equilibrium constant based on pressure. So if we look here we have sulfur trioxide is decomposed into sulfur dioxide and oxygen. So taking from the question, we have initial, so what we begin with. We have C, which is consumed, what is used. We have E for equilibrium, what is there at equilibrium. We have MF for mole fraction, and pp for partial pressure. So if we take from the question, we have 8 moles of sulfur trioxide to begin with, that's in our initial, and we produce 2.5 moles of oxygen at equilibrium. And if we have a look at the molar ratios, it's 1 to 2. So we know that there's 2 times as much sulfur dioxide as oxygen, so we can say that we have 5 moles of sulfur dioxide at equilibrium. And as you see, the molar ratio of sulfur dioxide to sulfur trioxide is 1 to 1, so we can say that 5 moles of sulfur trioxide was consumed to make these products, leaving 3 out of the 8 initial moles left at equilibrium of sulfur trioxide. So this is where the mole fraction comes in. Overall, we have 10.5 moles in this equilibrium, and our mole fraction is how many moles of this overall mole of each element. So 6 over 21 is 3 over 10.5. So the moles of sulfur trioxide over the moles total, and they're just times by 2 to get rid of the 0.5. And then we use these mole fractions to calculate the partial pressure, because we know that the overall pressure is 150 atmospheres, as it says in the question. So the partial pressure of sulfur trioxide is 150 times our mole fraction, our 6/21. And this 42.9 is the partial pressure. And we do that with the sulfur dioxide and the oxygen to get the partial pressures of each of the compounds in the reaction. And now how do we use them to find the equilibrium constant? So we have here the pressure of the products over the pressure of the reactants. And you can see here that when the compound had a 2 in front of the compound, we have squared them. So whatever the mole ratio at the front of the compound, we take as a power in the equilibrium constant. And if we sub in our partial pressures that we've just calculated, we can see that we have this equation, which we can easily do on the calculator, to find that our equilibrium constant is 98.8 atmospheres. So how do we interpret this equilibrium constant Kp value? So if our Kp is larger than 1, it means that the reaction favours the forward reaction. It favours making the products. And if Kp is less than 1, it means that the reaction favours the reverse reaction. It favours making the reactants.